So some good questions from Freddie and Josh, which they've taken some questions from the mock paper, which I think was made by In Thinking. So some questions here which we can think about. Have a look at them, pause the video, have a go yourselves, and I'll walk you through what I think the answer is to them. They've not been kind enough to provide the answers for me, so it's a good test as well. So the first question is comparing a voltaic cell and an electrolytic cell. A voltaic cell, of course, is one where a spontaneous chemical reaction is used to generate electrical energy, and the electrolytic cell is using electrical energy to force a non-spontaneous chemical reaction to take place. Now, these are just facts. So the answer is that oxidation does occur at the anode for both of them. So I'm not going to draw out the pictures here, but you need to be able to draw a voltaic and electrolytic cell and label the anode in both cases. And the anode in both cases is where oxidation takes place, and the way that I've taught you this is to remind you there's an O in the middle of the word oxidation, anode, which is kind of the clue that it's oxidation, and the cathode is always where reduction takes place. Delta G is negative for spontaneous reactions, right? So that one's true, by the way. Now, voltaic cells is a spontaneous chemical reaction, so delta G would be negative for that one, because delta G, remember, has to be negative for a reaction to be spontaneous, and it must be positive for an electrolytic cell, otherwise you wouldn't have to sort of turn on the plug to make it go, so that can't be right in my mind. And which is correct, so the cathode is positive and the anode is negative. Now that depends on whether you're talking about a voltaic cell or an electrolytic cell. The way to think about it, if you can't remember it, start with an electrolytic cell. This is the easiest one to work out. It's much easier to work this out. Whoops, there's a very bad picture of an electrolytic cell. That's the long line, which is a plus. That's the short line, which is a minus. We know the negative ions go to the positively charged electrode, and we know those negatively charged ions are called anions because they've got a minus in the middle of the word, and we know the positively charged cations, which conveniently have got a plus in the middle of the word, they go to the cathode. So you can remember that cathode is negative. And so that's easy to remember that. And it's the other way around for voltaic cells, so that ain't right either. So none of these make sense to me. So the answer is E, one only. So for this next question, have a little look at it. What do you think the answer is? When you take sulfur dioxide or sulfur trioxide, you end up getting acid rain. Acid deposition, a little bit on that, and standard level acids. Need to have a little read of that. I'll go back over that maybe. Write an equation including state symbols. Well, the sulfur trioxide, which is a gas, of course, dissolves in water. Now, Josh has made the point here: is water vapor not gaseous? Well, water vapor is gaseous, but rain is not gaseous water, nor are droplets in clouds. They are liquid water, little tiny droplets of liquid water, and so that's why it's a liquid there, and you end up with sulfuric acid there, which is dissolved in the water, so it's aqueous. There we go, that's that one. So, Josh, lesson of the day: water is a liquid, water in droplets is a liquid. Aqueous concentrated, there's the key point. Lithium chloride undergoes electrolysis, deduce the half equations. So have a go at that one. Now, the first thing to get right and get the marks for is what the products are. Now, lithium would go to the cathode. Lithium being positively charged ion would go to the cathode and might be discharged to form lithium. But under aqueous conditions, you need to know that that hydrogen would be formed in every case, really, except very low reactivity metals like silver and copper. So the answer is you're going to form hydrogen. So I'll come back to the half equation in a second. And at the anode, if it's concentrated lithium chloride or any amount of iodide or any amount of bromide, it's the halogen that forms. And that's what's happening here. So halogen forms from chloride. And if it was dilute lithium chloride or anything other than chloride, bromide or iodide, then you get oxygen forming. But the half equation here should be dead simple. So it's the chloride ions go to the electrode and become discharged to form chlorine. You could say discharged or you could say oxidized. But we need 2 chlorides to form a chlorine molecule. We've got 2 electrons there, and that should match what's in your data book. I think you'd get away with doing what you did at GCSE, where you took, so if you panic and can't remember, you'd almost certainly get away with saying 2 hydrogen ions combine with 2 electrons to make a hydrogen molecule. But let's make sure we've covered it as it's been taught properly. The reaction you should know is that it's actually water that's being reduced rather than hydrogen ions. And the reason for that really is because the concentration of hydrogen ions in water is of course minuscule. It's 1 times 10 to the minus 7 or thereabouts. And so the water molecules are turning into hydrogen, as I was saying. So we get half a mole of hydrogen and you get hydroxide forming. Of course, I've forgotten to add the electron in there. Sorry about that. Now, this would be what you would see written in your data book. So you'll be able to find that in your data book, that reaction, the conversion of water to hydrogen. It's a good reminder, isn't it, that the pH will increase when you do that reaction because you're generating hydroxide ions, or the concentration of hydroxide ions will be higher than hydrogen ions if you do this this reaction. So worth remembering that the pH changes when you do electrolysis, or it can change when you do electrolysis if you generate only hydrogen or oxygen. Tough question. Remember also that you have to be able to explain the formation of hydrogen or oxygen or chlorine, say, or bromine, using half equations and stuff. I'm not going through that now, but make sure you can do that if you really want to push those top scores. That's hard stuff, but hopefully you can do it. All right, a voltaic cell, we've got a zinc half cell and a nickel half cell. So to answer that question, you will need access to your data book and your standard reduction potentials. So there is an approach to working out this question using something called the anti-clockwise rule. It's not a rule I've ever really used or liked or taught. So if you want to look at the anti-clockwise rule, by all means find someone else to get your information from, but I'll walk you through how I work it out. So just to remind you here, we've got a voltaic cell made with zinc half cell and a nickel half cell. So the nickel half equation is nickel 2 plus being reduced with 2 electrons, and we've got a value of minus 0.26. What was the other one? Zinc, which is up here, same sort of idea, minus 0.76. So these values on the right hand side over here, they are in order, so you can use this anti-clockwise rule thing, which again, have a look somewhere else if you want to follow it that way. But I think of this as simply a measure of how far the equilibrium lies to the left or to the right. And it's not really a perfect way of thinking about it. It's all compared to the arbitrary value of 0 volts, which is when you attach any of these to a standard hydrogen electrode. Make sure you know what a standard hydrogen electrode is, even if you don't know the absolute details of what it looks like and how to draw it and stuff. But you connect any of these things to a standard hydrogen electrode, and this is the voltage you'll get, or the EMF you'll get. Now, this number, 0.26, is more positive. Sorry, minus 0.26 is more positive than this one, minus 0.76. So this equilibrium is lying more to the left. It means this reaction is kind of preferring to go left versus this one, which is preferring to go right. So if you were to connect a half cell of zinc and nickel, this one will go in the forward direction, and this one will go in the reverse direction, here like so. Okay. So that will give you an idea of what's going on. So the zinc is going to be oxidized, and this fits with everything we know. We can know from this that zinc is the more reactive metal. We know that more reactive metals become more easily oxidized than less reactive metals. And so it all kind of fits together. And so the nickel is turning, the nickel ions are turning into nickel, zinc is turning into zinc 2 plus. And let's go back to the question then. So it's asking what the overall equation is, and the overall equation, as I was just saying, was zinc turning into zinc 2 plus, and nickel ions turning into nickel. And you put the state symbols in there as well, and make sure it's balanced. It is balanced in this occasion because they're both 2 positive ions. Worth also thinking, you might be sometimes asked, which direction do the electrons flow through the external circuit? And think about that for a second before I answer it. So just to remind you, if you're going to get a positive voltage when drawing a voltaic cell like this, you've got a salt bridge there, and make sure you can label and draw this properly. I'm not doing it now. If you've got it set up properly with the more reactive metal, the more negative one on the standard reduction potential list on the left, you'll get a positive voltage up here, and then we get electrons flowing around in that direction. And also, when I taught you, I said that we always set it up with ox red, ox on the left, red on the right, so the other way around to redox, or the more reactive one on the left going through oxidation, and less reactive one on the right going through oxidation. Going through reduction. So electrons are travelling in the clockwise direction through the voltmeter, if you like, through the external circuit, which is a metal, delocalized electrons and all that, and going from the zinc electrode to the nickel electrode. And then the last one, chromium is used in electroplating. I really do think there's a chance that electroplating will be asked in your exam because it's a new topic, so make sure you know about it. And so the chromium is being used in electroplating, so we're going to be forming chromium at one of the electrodes. So we're going to have chromium ions being turned into chromium atoms. Now, either elsewhere in the question they'll be clear to you that chromium ions are 3 plus, or you'll remember it from using dichromate when we did oxidation of primary and secondary alcohols, or you can look in your standard reduction potential list and see there's chromium 3 plus ions in there. So at the cathode where reduction takes place, chromium 3 plus ions are going to turn into chromium atoms on the surface. Good to have state symbols here on the surface of that electrode. And presumably, if you want to make plenty of chromium ions so that they can go across the solution over to the other electrode, you're going to have chromium as your other electrode, and that's going to turn into chromium 3 plus. So I'll draw that so you know what that looks like. So let's say we're electroplating some piece of metal. There we go, a fork or something. Lovely piece of fork, lovely fork there, and we've got a power supply. And the cathode is the negative side, and we've got a lump of chromium there, and we've got a solution of chromium 3 plus ions. Those chromium 3 plus ions will travel to the negative electrode, to the cathode, and get reduced. They'll move that way, hit the surface of the electrode, which is the fork, become chromium atoms, and then over here chromium atoms will be replacing those chromium 3 plus ions. So the chromium atoms will become chromium 3 plus ions. Gradually, very slowly, this electrode, the anode, will be worn away, used up, disappear, and find itself on the surface of a whole bunch of things that it's being used to electroplate. Do get your head around electroplating, please, folks. Hope that was fun for you.